So I told you I would show you how you can memorize or how you can find the ratios or the side lengths of your special triangles. So if we see here, let's say that this right here, there we go. Oh, I see what I did. Let's say right here that this is a right triangle and that we have a 60 degree. And remember I said that's the same thing as pi over 3. We went through that in yesterday's lesson. And then right here, I'm going to have a 30 degree, which remember that's going to be the same thing as a pi over 6 angle. But I am going to only use one angle because I need to have space on the outside. But just as a reminder, that's what those two are equal to in radians. Okay, so let's say that this is what we have. The most important thing for both of your special triangles is that you're going to start by setting your smallest side equal to 1. This will also be true of your 45, 45, 90 triangle. In the case of the 45, 45, 45, 90, having your small side equal to 1 means both these sides are equal to 1. Because this is an isosceles triangle. Alright, so I'll come back to the 45, 90 though. What we have up here with the 30, 60, 90 triangle is just from this alone, it is difficult to figure out what the side ratio should be. So we're going to use a similar equilateral triangle. And with equilateral triangles, you may remember all of your angles are the same. They're all 60 degrees. So we can see here that this means that when we split the equilateral triangle in half, the triangle we started with represents half of our equilateral. So in other words, this side right here would be 1 long, and we can see half of our 60 degree angle is going to be 30. I know that this triangle on this other side is going to be identical to my first triangle, so therefore I know this side length also has to equal 1. And then very conveniently, because it's an equilateral triangle, because that entire side length now equals 2, it means these side lengths also equal 2. You can ask me questions about this if you have any places where you're not sure, and then of course watch this video as many times as you need to as well. Now that I know that this diagonal here is 2, I can take that and I can put it back on the original triangle. And once I know 2 sides on any right triangle, I can finish it out by using Pythagorean's theorem. So I'll do that right over here. I know that I have 1 squared plus this thing I don't know squared equals 2 squared. So that's going to be the same thing as 1 plus b squared equals 4. Subtract 1, b squared equals 3. Take the square root of 3. And I get that my final side is the square root of 3. So that's where that came from. I've used it often enough, I do have it memorized. But every once in a while I do have to go back to this original definition with the equilateral triangle to help me remember how to set it up. Alright, now for the 45, 45, 90, it's even simpler than that. We start, like I said, by setting your smallest sides equal to 1. Because you have two 45 degree angles, this is an isosceles triangle. So we can expect that this side length is equal to this side length when the angles next to them are identical. Then this one, I just go straight to Pythagorean theorem. I have 1 squared plus 1 squared equals c squared, because this time it's the hypotenuse I'm solving for, before I knew the hypotenuse. So I get 1 plus 1 equals c squared, or 2 equals c squared. Take the square root, and I get that that equals 1 square root of 2. So we do sometimes call the top of triangle a 1, 2 square root of 3. And we do sometimes call the bottom triangle a 1, 1 square root of 2 to define their ratios. Really properly, this one on top should probably be 1 square root of 3, 2, because the square root of 3 is smaller than the 2. But it doesn't sound as good. So if you have any questions about that, let me know. I'm not going to test you on that, but it's helpful to know with what we're working on.